Hello and welcome to lecture number 33 of the course Theory of Computation. This is the beginning of week 7 and also we are going to start chapter 4 of the SIPSA book. Right. So right now we are at the beginning of week 7, which is like exactly the halfway point of this course. Right. So in the previous lectures so far in week 6 we saw Turing machines. We saw different types of Turing machines, and then we saw Church-Turing thesis, and then we said that a decider is intuitively an algorithm, right? So, and we are going to try to understand what is computable and what is not computable, or in other words, we are trying to, our goal is to try to understand what are the things, what are the computational questions for which we have an algorithmic answer, or for which we can build a decider, and what are the questions for which we cannot build a decider, right? So towards that end, in this lecture, we will start with some languages, and these languages or these problems, as you can visualize them as problems, these problems will be based on other computational models that we have seen so far. So first we will see problems based on DFAs, and then problems based on NFAs, regular expressions, context-free grammars, and so on. And then slowly we will move into problems based on Turing machines. So and then the undecidable problem, the first undecidable problem that we will see, will be actually based on Turing machine, right? So first let us start seeing some examples of what I mean by problems based on regular languages or problems based on DFAs, right? So the first problem that we'll see in this lecture is A-DFA, right? So A-DFA means means acceptance problems of a DFA, right? So this consists of all the pairs, right? So it's a language where you are given a pair of so BW, where B is a DFA and W is a string, and you only accept those pairs that are where the DFA accepts the string, right? So it consists of, so A-DFA, the language consists of all the pairs BW, where B is a description of a DFA and W is a string where the DFA accepts W, right? And if you recall, in the previous week, in the last lecture, we said that given a DFA or an NFA or a Turing machine, we could encode the Turing machine and I could give you a description of the Turing machine, right? So here the problem, so when you see this as a decision question, it's like this. So I am giving you a description of a DFA and I am giving you a string and asking you, does this DFA accept this string? And that is the A-DFA question, or in other words, it's the acceptance question. So the A here stands for acceptance. So it's the acceptance question of a DFA. So this is the first theorem that A-DFA is decidable, right? So given a DFA and given a string, there is an algorithm by which you can tell that this DFA accepts the string or not, right? We want everything to be we are now going to see more and more from the lens of decidability. So the algorithms have to be deciders, meaning it has to hold regardless of whether the given string is in the language or not. So if it is in the language, it has to accept. If it is not in the language, it has to reject, right? So the decider is simple. So given a DFA and given a string, the decider, the Turing machine, what it does is it knows, so it is given the DFA. So it knows the rules of the DFA. And it just starts running the DFA on the input string, right? So suppose it knows that the string that is given is, let's say, 0 1 1 0 something, right? So now it knows the starting state, let's say Q start, right? Now it sees that if you read a 0, then you go to Q3, and if you see a 1 from there, perhaps it's a loop, right? So you are at Q3 again, and again the next is a 1, which is also, so you'll take the same loop and come back to Q3, and maybe the 0 now takes you to Q2, right? And then you check, so you have read the entire string, you made the moves of the DFA, right? So I'm just explaining how the DFA accepts, and then check whether this Q2, whether it's an accepting state or not, right? This is how you check whether a string gets accepted or not. And the same thing can be executed by a Turing machine or an algorithm, right? So if you tell the rules of the DFA and the string, the Turing machine can execute the DFA and check whether it ends in an accepting state or not. And if it ends in an accepting state, you accept. If it does not end in an accepting state, you reject, right? So that's it. So you simulate the DFA on the string and check where the simulation ends. So if it ends in an accepting state, you accept, otherwise you reject. If it ends in a non-accepting state, you reject. So it's pretty straightforward. You just simulate the DFA and then see what the DFA decides, whether it accepts or not, and then you reply. So there is no question of looping in the DFA, right? Because you are going to execute steps and at the end you are going to reach some place, right? So there is no question of looping. So it's a decider. So the next language is acceptance problem of the NFA, right? So it's slightly more involved, because a DFA, it's very clear, right? So you have a certain starting state, and given a starting state and a symbol, right? Let's say given a starting state, let's say QS, and there's a 0. Now earlier you knew that you are going to Q3. Now perhaps there may be multiple outgoing arrows labeled 0. Let's say there is a Q4, there is a Q7, all of them are labeled 0. So now there are multiple paths to track. How do you check whether a given NFA, right? So this is the acceptance problem of an NFA, A-NFA. So you are given an NFA and a string W, and you have to decide whether this NFA accepts the string, right? So but then, so instead of trying to keep track of all the possible movements of the NFA, we can do something slightly more. Of course, this can be done also, but we'll do something slightly different. But I think it's a bit more clever. So if you recall, when we learnt NFA the first time in chapter 1, we also learnt a theorem that says that NFAs are equivalent in power to DFAs, or in other words, we saw that given an NFA, you can construct an equivalent DFA, right? So if the NFA had, let's say, 5 states, the constructed DFA has 2 power 5 states. So basically, for every subset of states of the NFA, you had a state in the DFA, right? And then you made transitions accordingly. So again, I don't want to revisit the entire conversion process, but we saw such a result in the first chapter. So we can appeal to that result now, right? We can take the help of that result. So what I'm saying is that first, so you're given an NFA B, right? We can convert B to a DFA. So you can convert B to some DFA, let's say C, right? Using this conversion process. The conversion process was a very clearly explained process. So we follow that process and convert the NFA to a DFA, right? And once we have done that, once we have converted, so it's an equivalent DFA, right? So whatever strings are accepted by B will be accepted by this DFA, and whatever strings are rejected by B will be rejected by this DFA. So now let's say this DFA, the converted DFA is, let's say, say C is the converted DFA, right? Now all we are asking is whether, so C is equivalent to B. So now we are asking whether the DFA C, does it accept W? So meaning we have converted the problem of an NFA acceptance to a DFA acceptance, right? So we started with an NFA B. Now we are asking the question about, so B accepts W if and only if C accepts W. So now we have converted this problem to the first problem, that is we have converted into an A-DFA question, right? So now using that process that we just explained, we can simulate C on W and then decide whether C accepts W or not, right? So this is also decidable. So given an NFA B and a string W, you first convert the NFA to a DFA C, and then use the process that we already explained to decide whether C accepts W or not, and B accepts W if and only if C accepts W, right? So we check whether C accepts W and then say yes if it accepts W and say no if it does not accept, right? So what we did is we converted A-NFA to A-DFA, right? So this is something that This is a minor foreshadowing that I would like to do, because we will later formalize this notion of converting one problem into another. So what we did is we took A-NFA and the A-NFA instance. So we were given an NFA and a string, and we are asked whether this NFA accepts the string. We converted it into another problem where we have a DFA and a string, and the answer to this, the original question was yes if and only if the answer to this question was yes. So now we can as well answer the second question, but then we already know how to answer this question of the second type, where we have a DFA and a string. So this process of converting one problem to a different problem, this is called reduction, and we will formally see this later in the 5th chapter. But I just want to, for those of you who are curious, you may just make a mental note of this, and when we reach chapter 5, you'll be able to see it more formally, right? So we converted A-NFA to A-DFA, and now we know how to do A-DFA, hence A-NFA is decidable as well. The third thing is regular expression. So acceptance problem for a regular expression A-REX. So same thing, I'm not going to elaborate much. So you're given a regular expression R and a string W. The question is, does this regular expression generate the string W, right? Can we generate this string W from the regular expression? It's the same thing works. We also saw equivalence of regular expression to NFA or regular expression to DFA. We can convert regular expression to NFA and then use the decider for NFA. So now we have seen that A-NFA is decidable. So by this decider for A-NFA, we can decide a regular expression as well, right? So a regular expression is also decidable. Now after 3 acceptance problem, we'll see a slightly different problem called E-DFA. So what is E-DFA? Given a description of a DFA, we are asked whether does this DFA accept any string, or in other words, we are asking, is the language accepted by this DFA the empty language? So we want to check whether is there even one string that it accepts. Okay, so you may try to note that this is not of the same type. So earlier we got a DFA and a string, and we had to just check whether this DFA accepts this string. But here we are asking, does this DFA, is the language accepted by this DFA the empty language? Or in other words, is there any string that this DFA accepts? Even if there is one string that this DFA accepts, it is not the empty language, right? Because empty means it accepts no string. If it accepts no string, then it is the empty language. So that is what we have to decide. So maybe the first thought that comes to our mind at this stage is, let's do this. Let us start. Let us try with all possible strings, right? So we first try, let's say, small strings of length 1, then length 2, then length 3, and so on. We try each and every string. If any string is accepted, we say no, this is accepting some string, so the language is not the empty language. But then if it does not accept any string, then there are infinitely many strings, right? So you can have strings of length 1, 2, 3, 4, but then there are strings of all possible lengths. So at what point do you know that you are done? Right? So you may have to try out all possible strings, and there are infinitely many strings, so you will never be done. So if it accepts, or if it recognizes a language that is not empty, at some stage you see a string that is accepted, and then you can say yes, this does not accept the empty language, or you can reject the DFA because it does not accept the empty language. But if it does indeed accept the empty language or recognize the empty language, then you are never going to get a formal confirmation in this process, right? Because whatever you try, it will not get accepted. So when do you stop, right? So that's the question. When do you stop, right? So that way it's not very clear, right? So this, unfortunately, it's not clear. So we try a different approach. So what we try is, see, you have a starting state in the DFA, right? And maybe there are some transitions, let's say 0, maybe there is 1 takes you somewhere, maybe again 0, maybe self loop, 1 may be taking you somewhere else, and so on, right? right? So now again 0 may take you here, 1 may take you to some other state, right? And so the point that I want to make is, suppose there is an accepting state here, and suppose there is a path to the accepting state, right? Suppose this is labeled 0. So now we know that any string, the string 0 1 0 goes to this accepting state, right? Because there is a path here. Suppose, and we also know that the string 1 0 1 0 goes to this state, the accepting state, right? So 1 0 1 0 takes this path. So if there is a path from the start state to some accepting state, you know it is the language accepted is not empty. For the language accepted by the DFA to be empty, there should not exist any such paths, right? So all the, maybe I'll just use another color, all the accepting states, right? There should not be any path that kind of cross this barrier. All the accepting states should be on one side, and there should not be any way to reach the accepting states. So basically we are just asking, from the start state, is there a way to get to the accepting state? Is there some path, some directed path that goes to the accepting state, right? So if there is a path, language is not empty. If there is no path, the language is empty, right? So we just want to, so now the way is, now let us not look at it as a language or DFA or anything. We can just see this as a graph, right? So the key idea is we just view this as a graph, right? So this is the key idea. We just view the DFA as a graph, and we are just checking whether there is a path from the first vertex, this is the starting state, to one of these designated vertices designated as accept state, right? So this can be done with, there are many algorithms. I don't want to get into which algorithm, but then if you go to an algorithms course, there are many algorithms. You could do breadth first search from starting from the start state and see whether you reach one accepting state. You could do depth first search, right? Because it's a finite state machine, right? DFA is a deterministic finite automaton, it has a finite number of states. So you just run for some time and then you see which are the states that you can reach. And if it is reachable, if an accepting state is reachable, then the language is not empty. So you reject. If no accept state is reachable, then the language is indeed empty, and then which means you can accept, right? So we have seen 4 languages, all of which are decidable: A-DFA, A-NFA, A regular expression, and E-DFA, right? And in the textbook, you can check. These are written as theorems 4.1, 4.2, 4.3 and 4.4. So please have a look at these theorems, go through these theorems. Perhaps some of them I have gone through a bit faster. Maybe reading the theorems from the textbook may help your understanding better. Okay, so the next is EQ-DFA. So here what we are given is 2 DFAs, A and B, right? And we are asked whether these 2 DFAs are equivalent. In other words, we are asked whether the language recognized by these 2 DFAs, are they the same, right? So in other words, so if you think about it in the naive manner, you may be tempted to do this. Try out first string, the first small string, and you are checking whether is this accepted by A. Suppose the answer is yes. Is it accepted by B? Now if it is no, then you can say the languages are not same, because there is one string that is accepted by A but not by B. But if it is both accepted by both A and B, then you have to continue to the next string and then you do the same. Suppose the next string is rejected by both, again you have to go to the string after that and the string after that, and so on, till you find a string that is accepted by one and rejected by the other, right? But then this is also not a never ending process. Like if the languages are indeed the same, you will never get a string that is accepted and by one and rejected by the other, right? So that way we never are going to be able to reach a conclusion. If the languages are, if it's a yes instance, meaning if L of A is equal to L of B, you will just keep doing this but never end, right? So instead we use another way, right? So these are also again appealing to what we have learnt in chapter 1. So we know that regular languages are closed under union, intersection, complement, right? So these closure properties are going to be very useful. This means that if there is a DFA, let's say A, and it recognizes this language L of A, there is another DFA that recognizes the complement language, that is L of A complement. And if there are two DFAs A and B, then there is a DFA that recognizes the union of the two languages. There is a DFA that recognizes the intersection of the two languages. So that is what closure means. So given A and B, I can make a DFA that accepts the union. I can make a DFA that accepts the complement, everything is and the intersection, right? So using these closure properties, I can construct a DFA C, right, that accepts the symmetric difference of LA and LB. So what do I mean by symmetric difference? That I have represented here pictorially. So suppose LA is the circle on the left, right? So suppose this is LA, and suppose LB is a circle on the right. So this is a Venn diagram. Symmetric difference means the set of strings that are in LA but not in LB. So the intersection is removed, plus the set of strings that are in LB but not in LA. So we want the strings that are only in one language but not in the other. So in LA but not in LB, and LB but not in LA. So this will not include the strings that are in neither LA or LB, and this will not include the strings that are in both LA and LB. So this is the symmetric difference, this region and this region alone. So the mutual intersection is skipped. And so the symmetric difference is represented like this using union, intersection and complement. It is LA complement intersection LB, right? So which is this part. Union LA intersection LB complement, which is this part, right? So LA intersection LB complement is this, LA complement intersection LB is this, and it's the union of both. And since DFAs are closed under, or regular languages are closed under complement, intersection and union, we can construct such a DFA by all the closure properties. So if you remember all the closure properties, we proved by constructively. So to show that regular languages are closed under complement, we explained how to construct a DFA that recognizes the complement language, right? So we can make such a DFA C that accepts the symmetric difference of LA and LB. Now, when LA is equal to LB, what is the symmetric difference? So if LA and LB are the same, there will be nothing that is in LA which is not in LB, and vice versa. So which means that if LA is equal to LB, then the symmetric difference will be empty, right? And if symmetric difference is empty, then LA is equal to LB. So all that we are asking is, so we know how to construct a DFA which recognizes a symmetric difference. Now all that we need to know is the equality or the equivalence of A and B corresponds to the case when C recognizes the empty language. So this is yet another case where we are just referring to something that we have already done. We know how to decide whether a given DFA accepts the empty language. So now we constructed this DFA C, which recognizes the symmetric difference. And all that we are interested in now knowing is if the symmetric difference is empty or not. So we use E-DFA to decide, so we use the E-DFA decider to decide if L of C is empty. If L of C is empty, we accept, because if L of C is empty, we know that LA is equal to LB, which means it's a yes instance, right? The question was whether the two DFAs recognize the same language. If L of C is not empty, then you reject, because then that means that L of A is not equal to L of B. So that's it. even though I explained a lot, the procedure is very simple. You construct a DFA C using the closure properties, run the decider for E-DFA on C. If E-DFA accepts, we accept, and if E-DFA rejects, we reject. And E-DFA, the decider will certainly accept or reject, right, because it's a decider, it cannot loop. And that completes the 3 languages, or the 5 languages that I want to talk about, which are decidable languages based upon regular languages, right. So acceptance problem of a DFA, NFA, regular expression, the E-DFA asking whether a given DFA is empty or recognizes the empty language, and the last one is equivalence DFA asking whether the given 2 DFAs are equivalent, whether they recognize the same language, and all of these are decidable. And that's all that I have for lecture number 33. In the next lecture we will see problems from context-free languages. So this lecture was about problems from regular languages. Next lecture we will see problems from context-free languages. Thank you.